Hello, everybody. This is Sunday. It's July 17th, and we are heading into Module 11, Week 11 of our online astronomy course. Hope you're all doing well. This is going to be the last module concerning the stars. And modules 12, 13, 14 will be on galaxies in the universe. But in this module, we're going to be learning about the evolution of stars, how stars are born, how they live their lives, and how they die. Now, before I go on to talk about that, I want to mention that because this is the last module having to do with stars, that means that the week after this coming week will be your third exam. And just like the other two, you'll take it on Canvas, multiple choice, nothing unusual. But just let you know that is coming up during I think it's the last week in July. But Module 11. Oh, I will be showing you some of the first pictures released from the James Webb Space Telescope. But I'm going to do that at the end of this video, because some of what I'm going to be showing you are things you're going to be learning about in this module. And so I thought I'd wait until I talked about them just a little bit. So here we go, Module 11. In Module 11, you're going to be learning about the life cycles of stars, which astronomers call stellar evolution. Now, we use evolution in astronomy in a different sense than it's used in biology. In biology, evolution means that as a certain animal, a certain species of animal, as various generations of those go on, that certain individuals are more fit to their environment than others. And those that are more fit survive to go on to reproduce and have other later generations of that same species. And in that way, the characteristics of the species slowly change, and that is called evolution in the biological sense. In astronomy, we talk about the evolution of stars and galaxies to mean how a single individual star or a single individual galaxy changes over its lifetime. So you could think of your own personal life story as your own evolution in the astronomical sense. Okay, well, how do stars begin? Well, they begin with the collapse of a huge, vast cloud of gas and dust. And as that gas and dust, that cloud collapses under its own gravity pulling it inwards, it heats up. And as it heats up, the inside gets hotter and hotter until in the center, it gets dense enough and hot enough for nuclear fusion reactions to take place. And that's when the star is born. So how heavy and how light can stars be? Our star has a mass of 1 solar mass. That's just what we call the mass of our sun. The least massive stars have a mass of about 1/10 of the mass of a sun, 1/10 of a solar mass. And these stars, if you get any less massive than these stars, they can never get hot and dense enough in their centers to begin nuclear fusion reactions. Now, how heavy can stars be? Apparently, they can get as heavy as 100 or 200 times the mass of our sun. And once you get up to masses like 100 or so solar masses, those stars are so bright and so hot that they literally start to blow their surface layers out into space. And so they suffer a lot of mass loss. And you'll learn about that in this module as well. So stars are born between 1/10 of a solar mass and 100 or maybe 200 solar masses. And stars begin their life on the main sequence of the Hertzsprung-Russell diagram. That diagonal line that runs from the upper left down to the lower right in the Hertzsprung-Russell diagram, the HR diagram. Now, the the stars that have lower mass, about the same mass of our sun and below, get their energy by fusing 4 hydrogen nuclei, 4 protons, into a single helium nucleus. And that step of reactions you learn for our sun is called the proton-proton chain. And that's what powers our sun and stars that are less massive than our suns. But stars that have twice the mass of our sun or more are powered by another series of reactions. And again, the net effect is to bring 4 hydrogen nuclei, 4 protons, to form a single helium nucleus. But they do it by hitching a ride. Those protons hitch a ride on carbon and nitrogen and oxygen nuclei. And so the carbon and nitrogen oxygen nuclei are used as catalysts to bring those 4 protons all together and form a helium nucleus. And that's called the CNO cycle. And so stars from a little bit more massive to as massive as stars can be get their energy by changing hydrogen into helium through the CNO cycle. Well, so that's what powers stars on the main sequence. How long do stars live on the main sequence? What is their main sequence lifetime? Well, that depends upon 2 things. It depends upon, first of all, how much fuel a star has for these nuclear reactions. And that fuel is hydrogen. And so it depends upon how massive a star is, on how much hydrogen the star has to burn. Now, when I say burn, astronomers use the term burning as shorthand for nuclear reactions. So whenever I say burning, that's not burning in the sense of a piece of wood or a match would burn, because that means combining with oxygen, and that's not involved here. We're talking about nuclear reactions, nuclear burning, and the bringing together of lighter nuclei to form heavier nuclei and so release energy. So a star's lifetime on the main sequence depends upon how much mass it has, how much nuclear fuel it has in its center. And it's in the center that counts, because that's where the nuclear reactions take place, where it's dense and hot enough. The other thing that counts toward a main sequence lifetime is the star's luminosity, which is how fast it uses up that fuel. You know, if you want to know how far you can go in your car, what matters is how much gas you have in your tank and how many miles per gallon your car gets. That'll tell you how far your car goes. Same thing for a star. It's how much hydrogen fuel it has in its central tank and how quickly it uses up that energy, how quickly it uses up that hydrogen, and that tells you, is told by the star's luminosity. Our own sun has a lifetime, a main sequence lifetime of about, roughly 10 billion years. Our sun and Earth, as you know, are about 4.6 billion years old. So we are about halfway through the sun's main sequence lifetime. Now, a real heavy star, like the star, let's say 15 times the mass of the sun, that has a lot more fuel to burn. But the star is much brighter than the sun. And so its main sequence lifetime is very short. In fact, a 15 solar mass star will end its lifetime in 15 million years. A lot shorter than the sun's 10 billion years. On the other hand, how about that little half solar mass star? That star has much less mass than the sun has, only half as much mass, but it has a very much lower luminosity. And that means the lifetime on the main sequence of an M star is 200 billion years. That's much older than the age of our universe. And so every M star that has ever been formed is still on the main sequence. So as stars age, if you have a bunch of stars formed at the same time, like in a star cluster, And those stars will initially lie on the main sequence of the Hertzsprung-Russell diagram, but then the short-lived stars at the top of that will peel off first. And then the lower mass stars and lower mass stars and lower mass stars and so on down will leave the main sequence. And what happens is as stars continue burning, eventually they're going to run out of hydrogen. And then what happens? They start burning helium. And again, by burning, I mean the nuclear fusion of helium nuclei. And what happens is that 3 helium nuclei fuse together to form a carbon nucleus, or perhaps 4, it can pick up another one to produce oxygen. And so the fusion of helium, 3 or 4 helium nuclei come together to form carbon and oxygen nuclei, and that releases energy. And that powers the star through its next stage of life. Now, early on, when helium nuclei were first discovered, people didn't know what they were. They didn't know they were the centers of helium atoms. So they called them alpha particles. And so what happens is that 3 alpha particles come together to form a carbon nucleus. And that reaction is called the triple alpha reaction. So what happens as these stars start burning this? They're burning this takes place at a hotter temperature. The fuel is used up more rapidly. The central core actually shrinks a little bit, while the outer part of the star expands and cools, because as the gas expands, it cools. So what happens is that as the star ages and goes off the main sequence, it becomes cooler, and it becomes larger, and it becomes a red giant star. And if a star has more mass, it will start burning carbon and oxygen and heavier elements, all the way up to iron. But once you've produced iron, you cannot bring iron nuclei together and release energy that way. Iron is the end of the fusion chain. And so those stars that end up with an iron core are among the very brightest stars there are. And those are the supergiant stars, the red supergiants in the upper right-hand corner of the main sequence. Now, along the way, there's some really interesting things that can happen, is that the stars go through a stage where they become unstable. It's called the instability strip on the HR diagram. There's a picture of it in your book. What happens there is that the stars begin to breathe in and out. Now, they're not literally breathing, they're not living organisms. But what happens is that their surfaces expand and then contract, and then expand and then contract. What that means is as they contract, they get hotter and brighter. As they expand, they get cooler and dimmer. And so we can watch these variable stars, these pulsating stars. We can actually watch them. Some of them have very short periods, a period being the time for one expansion, contraction, and expansion back to its starting point. So the time for one cycle is called the period. And that can have a time from just a couple hours to hundreds of days. And that may seem like, well, that's interesting, but so what? Well, these stars give astronomers the key to unlocking distances in the universe. These are probably the most significant types of stars ever discovered. And they were discovered by a woman. Well, people knew that these stars pulsated, but what that could do for astronomy was discovered by an amazing woman named Henrietta Swan Leavitt back in the very beginning of the 20th century. And she was watching these stars all at the same location. She was watching them in the Large Magellanic Cloud, and that's a neighboring galaxy to our own Milky Way galaxy. And she noticed that stars that were brighter took longer to go through one bright, dim, bright cycle. Stars that had quicker, shorter periods were dimmer. Stars that had longer periods are brighter. And so she discovered this period luminosity relationship. And that unlocked the key to distance, to the stars. And here's how it works. You can just look at a star out in the sky, and that tells you the star's apparent magnitude. But if you measure the period of the star's oscillation for these pulsating stars, that can tell you how bright the star is really. It tells you the star's absolute magnitude. And as you found out in the last module, if you know the star's apparent magnitude, that's little m, lowercase m, and you know the star's absolute magnitude, that's the capital M, you can find out the star's distance in parsecs. And so you'll be learning how to do that in this module, and there's some homework exercises in your homework quizzes for doing that. So finally, how do stars end their lives? How will our star, our sun, end its lives? Well, low mass stars, by low mass stars, I mean stars that start out with about 8 times the mass of our sun or less, 8 solar masses or less. Well, eventually they will never get hot enough to go all the way up to an iron core. They are left with a carbon and oxygen core. And what happens is that they puff off their outer layers. And that's what's happened in this image behind me. This is an image behind me of a planetary nebula. Now, it was called a planetary nebula because when they first saw it through crude telescopes, they thought, well, maybe that's a planet. But it's not. These are the outer layers of this central star right here. They're the outer layers of this star that have been puffed out into space. And that leaves behind the carbon-oxygen core of that star right here. And that is called a white dwarf star. There's no fusion going on in that star, no nuclear fusion. It's a dead star. All it can do is cool off with time. And it's held up by something called electron degeneracy pressure. You may have heard that you can't have 2 things in the same place at the same time. Well, electrons are like that. You can't have 2 electrons in the same location at the same time. And that means the electrons, when this core shrinks down, they resist being pushed together. And that creates an electron degeneracy pressure that holds up that white dwarf right there. And so that's the ultimate fate of our sun, to become a white dwarf. And over billions and billions of years, our sun will cool off, and so it becomes very, very dim, very cool. And what happens to carbon as it cools off like that is that it crystallizes. Now, what's crystallized carbon is diamond. And so our sun will be like a diamond floating in the sky. Now, as it turns out that the structure, the crystalline structure of the carbon isn't exactly the same as the diamond you might see on a piece of jewelry. But still, you can think of our sun as being a diamond floating in the sky at the very end of its life after billions and billions and billions of years go by. But how about Earth? What happens to Earth? Remember that as stars leave the main sequence, their outer layers expand, and eventually the sun's layer will expand past the orbit of Mercury, past the orbit of Venus, swallowing those planets, and right out to the orbit of Earth. And so Earth's seas will eventually boil away. Its atmosphere will be blown away. And there's a white dwarf here. All there's going to be is a dead cinder of Earth, perhaps still orbiting it. That is still billions of years away. So please don't worry about that. That is 12, when the sun is 10 to 12 billion years old, and we're not even halfway there yet. So don't worry about that. Now, the most massive stars greater than 8 solar masses, they end up with an iron core. And what happens when fusion ends and that, all the iron has been produced and you can't have any more fusion? Well, what happens is that core collapses. It collapses. And that core has an onion skin structure. On the outside is iron, and inside of that is magnesium and silicon and carbon and oxygen, all sorts of things. They're at the same time, and as this core collapses, it undoes all of those nuclear processes that form those nuclei and breaks them down into just neutrons. And neutrons can't be squeezed together either. And so there's a dense core of neutrons that forms about the size of Ogden, really, just 10 or 15 miles across, 10 or 15 kilometers across. And that dense core of neutrons forms. Now there's still other stuff falling in toward that core. It hits the core and it bounces off. And the result is a huge explosion that we call a supernova. Excuse me. I have to get a drink of water. Iced tea, actually. So the outer layers of the star bounce off that neutron core, and the result is a supernova. It's one of the most spectacular things that can happen. Now, maybe though, that core is so massive that even the neutron degeneracy pressure is defeated. And in that case, you end up with a black hole. A black hole is a region of space that is forbidden to our exterior world. It's a place where at the surface of a black hole, now a black hole doesn't have a material surface, you can't stand on it. What I mean, it's just a location in space around that black hole. And at that location, the escape velocity to get away from the black hole is equal to the speed of light. And as you know, nothing can go faster than the speed of light. So inside that region, around the center, nothing can escape from it. And that's why black holes are black. Nothing can get out. That surface that I've been talking about is called the event horizon. And there's something else that happens at the event horizon of a black hole, and that is if you have a watch, and if you were an astronaut and you were to hold up a clock or a watch, and I was to push you toward that black hole and watch it as you fell in, you would see that clock, as the hand goes around, goes slower and slower and slower until right at the surface of that black hole. And by that, I mean right at the event horizon, when that person I pushed in, maybe I'll push in a robot, make it a little bit more humane. As that person reaches the event horizon, they're frozen there because time has stopped at that location. And so where's all the mass of that object that collapsed to form the black hole? That's at the very center, at a point that's infinitely dense, and that's called the singularity. So you learn all about white dwarfs that are about the size of Earth, neutron stars that are about the size of Ogden, a small city 10 or 15 kilometers across, or for the most massive stars, they'll end up as black holes. And you'll learn all about these in this module. So this is incredible stuff. And we have seen many black holes. We have even seen the gravitational waves that are created when two black holes collide with each other. And you can have a binary star system. Each of those grows big, they become a black hole. And as they orbit each other, they send out ripples in the structure of space called gravitational waves. And as those two black holes come in and merge with each other, you get a huge burst of these gravitational waves, and then we've detected those on Earth. We've also detected the gravitational waves from two neutron stars coming together and combining to form a black hole, or exploding as a new type of nova. And a nova is something else you'll learn about in this module. So a lot of stuff in this module, and I've just given you sort of a preview of what's to come. Now, I do want to talk a little bit about the James Webb telescope. The first pictures, you've probably seen some of the pictures, but I want to just show them to you. And I want you to remember that what's different, what's special about the James Webb telescope is that it's so large, and so it can see great details in the images it takes. And it sees mostly infrared light. This is the spectrum of light, the electromagnetic spectrum. And you can see that here is what James Webb sees. It's infrared light. Hubble could only see visible light. But the James Webb Space Telescope, or JWST as I'll call it from here on because it's a lot easier than remembering James Webb Space Telescope, JWST sees infrared light. So let me just show you a little bit of what was seen, and I'll just go forward here. And this is one of the first images that the Space Telescope sent back. This is a cluster of galaxies that's about 4 billion light years away. There are a few objects that have these diffraction spikes, these 6 diffraction spikes. And these are due to the way light bends around the struts holding the telescope together. So here's a nearby star in our galaxy. Here's a nearby star. There's one, there's one. You can find more yourself. But everything else in this picture is a galaxy. That's about 4.3 billion light years away. This is a very massive cluster of galaxies, so massive that it can create a gravitational lens. Now, gravitational lens is where something massive, it's mass that causes space to curve around a black hole. It's the black hole's mass. And the cluster of galaxies also has a lot of mass. It can do the same thing and act as a lens. And so these weird little deformed galaxies, these orange galaxies, are far behind this cluster of galaxies here that's only 4.3 billion light years away. In fact, the most distant of these galaxies, the most distant is about 13.1 billion light years away. And that light started out to us when the universe was less than 1 billion years old. And so this is really exciting for astronomers to be able to see images, although distorted, of these very, very distant galaxies. Here is another case of a planetary nebula. And right at the center here is a white dwarf star, like we were talking about. Now, this image from JWST was taken in the near infrared, near visible wavelengths. But if you go to the middle infrared range, of longer wavelengths, you can see deeper in, and you see that white dwarf has a binary companion. And you can also see the dust that has been ejected from this binary system, these trails of dust. And down here at the bottom, you can see the scale. This is about 1/4 of a light year. Now, this is a collection of 5 galaxies. They're in the same part of the sky. It's called Stephan's Quintet. And this image was taken by the Hubble Space Telescope. Now, only 4 of these galaxies are close to each other physically. And so they're interacting each other with their gravity. And those are the 4 that look sort of golden. This 5th galaxy over on the left is really much closer. It's about 4 million light years away. And so the 4 that are really interesting are these 4 that are golden. This is a Hubble Space Telescope picture, but I wanted to show you this so you could see what they look like in visible light. And here is the picture taken by JWST. You can see, looking at these 4 galaxies right here, especially these 2, you can see that these 2 galaxies are interacting, and then this 3rd one up here is interacting with these other 2, and where they are colliding, you can see this hot gas, these arcs of hot gas around the galaxies. And this is going to be very interesting for studying this system. Moving a little bit closer, this is about 7,500 light years away. This was taken at a combination of the near and the mid-infrared by JWST. And this is the Carini Nebula. This is an area of very active star formation. And you can see all along here that there are little places where there are active stars. These are hundreds of stars in here that we've never seen before. And you can also see this reddish glow here is actually gas that is streaming off of this nebula. And it's being driven away by those young, hot, bright stars that you see. Now, this is really interesting to me. This is not an image. This is a spectrum taken of the atmosphere of an exoplanet, a planet around another star. And it has been a terrible challenge, a hard task to try to take a spectrum of those atmospheres because we're looking for water. And here in this spectrum, you can see very clearly, this is just showing the signal from all of the elements that are in the atmosphere. You can see these high points here from water. Here are 2 others over here from water. There's another one from water. But these signatures of water in the star's atmosphere are not signatures of liquid water, but rather steam. This planet is very close to its star, and its atmosphere has a lot of steam in it. And this is going to be a big, important tool to use for studying the atmospheres of planets. Finally, this is a picture of the near-infrared taken just of Jupiter. And I think this was taken on the way out to its final location, because at its final location, the telescope couldn't point back toward the sun. But still, Jupiter is away from the sun, so I'm not sure where the spacecraft was, where it took this picture. But anyway, you can see, look at the great red spot, really glowing hot there, really glowing bright at these near-infrared wavelengths. And people have wondered why that is, because the red spot is actually a little bit higher than the surrounding atmosphere. That means it should be colder, but there's so much turbulence in that red spot that it's sending sound waves up into the atmosphere above it, and that heats the atmosphere. And check it out, you can also see Jupiter's faint ring. going around the planet. So that is pretty cool. And there's going to be so much more coming back from JWST. That's going to make this a really exciting time in astronomy. Now, as we always do, I want to go to Stellarium to show you just what's in the night sky this week. So let me do that. I will just take a look at Stellarium here. Here it is. This is the night sky as it's going to be. This is either very late Monday night or very early Tuesday. This is actually 2 a.m. on Tuesday the 19th. And Tuesday is the day of the first quarter moon. And you can see that the moon is very close to Jupiter here in the sky. So there's early in the morning on Tuesday. And if I go forward just a couple days, so let me do that. I'll go forward a couple days. So here's the 20th, 21st. You can see on the 21st, it's going to be very close to Mars. So if you want to see the third quarter moon, it's third quarter on Tuesday. But if you want to see the third quarter moon very close to Jupiter and Mars, you can go out early in the morning if you want to get up for that. All you have to do is look in the sort of the east-southeast part of the sky. Well, I hope you enjoy learning about the life story of stars, the story of stellar evolution, how stars are born, live their lives, and die. As always, if you have any questions, give me a call. I'll be happy to set up a meeting on Zoom or in person. So until next week, bye-bye.